Greetings 2021ers. This video will walk you through Lab 12 and demonstrate several different optimizations that you're likely to want to add to your project for some diag benchmark. That optimized version of the function that you're implementing will need to include several things. The preamble to the lab mentions several of them, and these will all appear in the lab code. They include replacing repeated memory references with local variables. We'll see how that's done. Replacing function calls with macros, or macro invocations. This will inline the code rather than jump control around. And unrolling a loop at some factor level, which tends to benefit the processor pipeline and multiple ALUs in superscalar processors. Since modern processors have both those features, you tend to get some benefit from doing this. This will also be a good chance to demonstrate the use of C's macro system. It's a sort of glorified copy-paste or programmatic version of that thing, and you've been using it for quite a while through the use of the pound include directive, but we'll see what it's good for aside from that. I'm going to copy the link to this code up here because I'm going to log in to one of the remote servers and download the code there. Let's see, the server that I'll want to make use of is login01, so SSH into that. I had heard that some of you are having trouble getting into that. You can always SSH, for instance, to Atlas or one of the Keller Hall 1250 Labs machines, and then go from there to login01 or 02 or 03. As I proceed here, I'm going to have to get that code someplace, so let me move over to a CSCI 2021 directory. I think I might have a version, an older version of the Lab 12 code here. Yes, I'm going to get rid of that, and then do a wget on this, which will download it. I can unzip that code, so there's Lab 12 code over there. And get my usual things, and at this stage I'm probably going to want an editor of some kind to start looking at these things. My editor of choice is Emacs, which runs fine in the terminal. I'll pop open a directory view here and then also get a shell set up over here. So right hand side over yonder will be shell stuff, left hand side will be directory stuff. And I'm going to bop then into this Lab 12 code as well as change that terminal in there. So as usual, there is a questions.txt document here. So I'll fire that up. Usual preamble for stuff and a mention up here to log into one of the login machines to make use of those facilities, which will then match any of the timing expectations that are present in here. The things that we'll be looking at here are within this function v macro.c program. There are several versions of the same function that sums up elements of a matrix row, called progressively sum rows func p, func s, macro, and unroll 4. We'll have a look at each of those. The first step to working on this lab is to complete each of these functions, as they have some stuff that is intentionally left out for them. And so if you tried to, for instance, build things at this stage by typing a make, you get a whole litany of compiler errors because there are these little question marks in there which are meant to be filled in with code that you are to place in. So let's pull up that bit of code. It is in funcvmacro.c. So what you'll notice towards the top of this is there are a couple little getter and setter functions. We'll be working out of the same basic data structures that are present in the project. So there's a matrix T type and a vector T type, but they're really glorified arrays that the primary field of this mat is a data field, and it's just an array that allows you to access elements of the matrix in a sort of long contiguous array. And just a little bit of arithmetic is done by multiplying the row, or sorry, the row that you're interested in by the number of columns, so that's elements per row, and then adding on the column number to get it. Likewise, the vector stuff just involves an array that's called data as well. So this is typical of object-oriented programming, where you would have these little getters and setters that access parts of stuff. And the first thing I want to do in order to measure the performance of all this stuff later is to fill in uses of those. So for instance, here in this function, which is going to sum up the elements of each row and then set this output vector, vset, to be of those, I'll need to grab out an element of the vector using that mgetP function. So that's the to-do item here. I've got a sum that's 0 here, so I'll say something like sum plus equals, and then I have to get out a particular matrix element. Here I'm in a particular row and then working across a column, so I pass in then this mat pointer, matp, that comes in as an argument, and then the row number and the column number, and call it a day. And this will progressively work through a row, add up elements onto sum. And when I have that sum up, I'm responsible for setting one of the elements of sums p to be that. I'll make use of this vsetp macro for that. So here's vsetp, and the vector I want to set is this sums p vector. P. I want to set the ith element, because that's the row I'm in this outer loop, and then I'll set it to the sum over here. Now if I were to pop back over to the shell and recompile, there's nothing apparent at the bottom here, but up towards the top there'll be fewer errors in many respects. Let's see, a function mget, oh, I have a little typo here, it should be an mgetS rather, that line of code. So you have mgetP, rather. We'll get to the S version. Okay, and that should then resolve all the errors for this portion of the code. I could try to comment a bunch of things out and then sort of test the code. Would be a good software engineering practice, but most of these to-do items are pretty straightforward. Now down yonder is a very similar version. I'm going to see if I can get this stuff here to be on screen along with the other stuff. Yeah. Okay, so in between this row sums func p version, the p is short for pointer, there are a couple of additional getter setter functions, but you'll notice in this case works with a struct. No stars involved, so it's an actual struct. Thus the dot instead of the arrow over here. And the point of this version 2 is to try to not hit main memory as much through dereferences. And each call to this function will pass a pointer. Each function call will need to dereference. That's that arrow operator. Instead, it would be nice to be able to do all this stuff, ideally in registers alone, or at least in local variables. And so the first few lines of this row sums func S version, which is short for structs or actual structs or local structs or whatever, is to dereference those structs, which will copy all the fields into local variables, ideally registers over here. To that end, I just need to make slight changes here to what I had previously. This sum up here that was passing in a pointer to this matrix structure. I can do so here, but this time I'll call the mgetS version and then just pass this this mat was declared up there. And similarly up here, I'll grab this vsetp and copy it down and just make some minor adjustments. This is the vsetS and the sums on its own version here. Now, interestingly, copying the entire struct from the pointer into this local over here copies any pointers that are present in this struct, so we can sort of get away with this and everything works out all right. But in the wider world, not necessarily in this class or this project, you want to be a little bit careful with that because you've got two distinct copies of the struct, one that's associated with this pointer, one that's now local to the function, but we're getting away with this in many respects because the local copy has the same pointers in it as the sort of pointed to version over here. If that subtlety is a little hard to grasp, don't worry about it too much for now. Okay, if I jump back over and just check to make sure I spelled things right, we can now get only a screen full of stuff. That is errors, and we're looking to move on to 88, nothing above any question marks over here, so we're making nice progress so far. We'll look later at the implications from performance of why one might do this. But you should have some suspicions that if you if dereferencing oftentimes hits main memory and costs you some time, then dereferencing once at the beginning to try to get this into registers is going to be better ultimately than dereferencing each loop iteration. This would be the case here. The ultimate version of this is to move things into macros. Now, these capital mget and vset are somewhat different than what has preceded them. Let me get those down at the bottom here, and we can compare them to the function calls up here that are most similar. You can see that the syntax is wildly different here. This is what's known as a parameterized macro, and we'll look at some variants of it shortly. But it should strike you as quite different than the function version that's up here. And don't mind all of the parentheses and so forth over here. Writing parameterized macros like this are a little bit, it's a bit of an art form. It takes a practice, and you're not expected to do it right now, but you are expected to learn the meaning of why we would use a macro like this, go to the trouble of writing this garbage here, and what effect it has. That's part of what this lab is going to teach you. At any rate, it's conventional to have macros defined in uppercase, so capital mget here and capital vset here. But you can see they take things that look sort of like untyped parameters. So to that end, we're going to make use of them just like functions. And on that note, I may as well just copy this sum plus equals here because we're about to make use of it. Down here, I'm going to make use of the macro version of this instead. Let's see. Paste that part in over here. And all I really need to do is uppercase this thing, and I should be in business. Similarly, I'll grab the vsets here and uppercase that. I jump over and do a make. Oh, let's see, spelling errors. Oh, there's no S in the macro version here, so mget versus vset. So that should do it. If I make again, we're down to just a few sort of question marks to fill in. Finally then, we'll see momentarily that this macro thing does something interesting that's distinct and different than function calls and enables some greater performance here. So finally then, there is an unrolled version of this that we're to make use of the macro stuff, but this requires just a little bit of explanation. So looking at this code, you can see it's somewhat longer than the preceding version, and I may as well get that up on the screen over here. So here's the macro version. It says, have a double nested loop, outer loop goes over rows, inner loop goes across a row, and basically I'm marching across that row one by one. Similar sort of setup over here, however, this loop that goes across a row, it now goes not by ones, but by fours instead. And you'll note down here there's a second loop that goes by ones. The meaning of this is that we're going to duplicate some code here. Generally not a good idea, but this is a somewhat interesting and important optimization to be tangentially aware of, called loop unrolling. And you can see, hopefully from the pattern, what I'm going to want is a sum 0, sum 1 plus equals something at j plus 0, j plus 1, and the loop unroll factor that's dictated here. This will be 4 times, so I'm just going to copy and paste this thing as a number 2 and number 3, and then change the offsets from j in accordance with that. So sum 2 and sum 3. There. And maybe just because I'm nitpicky, I'll move my to-do up here. So this iteration through the loop going 4 at a time is interesting. And part of the reason that it's going to unlock some potential is that each of these variables, we're adding into them separately. And to that end, I can add on to some 0 without needing to interfere with some 1 or some 2 or some 3. And we observed earlier when we were studying the processor pipeline and its superscalar features that when you have independent operations like this, they pipeline very nicely and can potentially exploit multiple arithmetic logic units to do the operations in parallel if they're available. So to that end, this is potentially going to lead to greater performance, albeit with some trouble here. For instance, I don't know for sure if an unroll factor of 2 or 3 or 4, as is the case here, is going to be optimal for a particular architecture. And if you're doing this by hand, you have to sort of guess and check. Now, since I've set up this lab, I know 4 works pretty well here, so I'm not going to misguide you there. But on the project, you may want to try sort of different factors here. Secondly, as you're going by 4s here, not every sort of row length is going to be divisible by 4. So you have to be careful, A, not to go out of bounds, so I'll prematurely terminate this loop before I could potentially go out of bounds. And you can think of this as like, oh, if I didn't have something like this and a j was 0 and I had only 3 columns per row, then I would wantonly sort of go through and add on the 0th, the 1th, the 2th, and the 3rd element, even though that this 3rd element is actually off of the end of the row. So to that end, having termination criteria like this that are somewhat less than what you're going for is good. And since then those end elements are not evenly divided into the rows, you'll usually have a little cleanup loop or finishing loop at the end here, which requires a little coordination. So you'll note here j is declared outside the scope of this for loop, so that as it counts up and becomes 4 and 8 and 12 and 16, then it stays 16 after the loop finishes, and I could start getting the 16th, 17th, 18th elements in an unevenly sized loop here. Just going by ones here. So there'll be relatively few iterations here, sort of like 0 to 3 iterations. So most of the performance gain comes from up here. Interestingly, going by 4 means fewer comparisons and fewer branch predictions as well, which oftentimes helps with performance, because anytime you have to guess, am I jumping out of loop or continuing the loop iterations, this is a hazard in the pipeline. So reducing the number of those that are encountered tends to beef up performance. All right, for our remaining question marks, we have a sum 2 and a sum 3 down here. So we'll just introduce those up here. And, sum 2 equals 0 to begin with, and sum 3. And the last step then is to do a macro invocation to set a particular element of the vector, the sums up here, to be something. I'm going to jump over on this right-hand side where I had that v set over here. In our previous version, this is just row sums macro version, we had only a single sum. Now I've got a sum 0, sum 1, sum 2, etc., so I'll just add those all together, because in total they should be the sum of everything in this row. 3. Okay. Now, unless I'm badly mistaken, this should be all of the problems, or sort of fill in the to-do items. And if I search, yeah, there's no to-do items below this. So we're good to go there. And we can actually run this code now. So if you look at the main down here, it's oriented as a benchmark. And you can draw some inspiration for this as you would work on other things, for instance, your search benchmark. But the structure here is very reflective of stuff like what's in your sumdiag benchmark. That there's some specified number of times that function calls are repeated in order to scale up the time. In this case, it's plenty to do 50 iterations so long as your matrix is big enough to sort of observe lots of those effects. And then a bunch of clock variables here, which are used to start a timer, repeatedly invoke a function, stop the timer, and report the time, and then repeat that for the other functions. For instance, the first one that's up here was the row sum func p, and then down here the row sums s, and then the row sums macro, etc. And so we'll see the times for those printed over here. I do have to specify a matrix size, so I'll call this as func v macro. And so maybe I'd pick something like 100 rows by 1,000 columns, and I get some, middling sort of smallish times over here. And I may want to bump this up just a little bit, so maybe I'll say 100 rows by, I don't know, 10,000 columns or so. Okay. Let's see. I'm noticing a minor mistake in the make file. And since I haven't published the lab yet, I'm going to make a correction to that make file. So hang on just a second. Okay, had a minor fix to make. Tuning these kinds of exercises to new hardware with different versions of the GCC compiler on it that do slightly different things than old versions is terribly painful. And so it took me a little while to find the right combination of options to get the learning exercise oriented in the way that I wanted it. Let me just quickly then do a make clean. That's because we'll recompile with some new options. That'll be there in the make file for all of you, but I sort of botched just a little bit here. So I make again, and then run this on a modest size matrix. You'll see some times here that indicate a certain ordering of speed, which is more or less what we're aiming for. That the first version is the slowest. The second version gets a little better, the third version is better yet, and the last version is the fastest. This should be true on a range of different matrices, so I can't control repeats, but I can control size. So for instance, I'll bump up the size here to 1,000 rows by 10,000 columns. That should make things go about 10 times, take time 10 times as long, but we get roughly the sort of same ordering and magnitude of times over here for this stuff. Which brings us then back to the questions.txt document. We've done all the to-dos over here. We're getting times that output that are realistic over here rather than these faux times over here. And let's see, I think I had run, I'll run this exact invocation down here just so we have the sort of times that are asked for in the quiz that we'll sort of look at momentarily. And yeah, they're sort of more or less the same thing because it's all factors of 10 here. Okay, so then we're in a position to start answering questions about this stuff and have to decide on an ordering for each of these. As we're observing, V1 is the slowest, followed by V2, followed by V3, followed by V4. And consulting over here in the questions.txt document, this says V4 is slowest, definitely not. V4 is slowest, definitely not. V1 is slowest, followed by V3. That doesn't seem like the right ordering, but this goes V1, V2, V3, V4. That's looking pretty good. So I'll select that as my quiz answer. Now the ordering of code transformations that we did is one that you may want to engage in for your project. And the remainder of the quiz questions grill you about exactly what's going on and why, and particularly why it's going to improve performance. So answers here may be useful as you're constructing the description of optimizations that you must provide for your write-up for that SumDiag benchmark business. So we'll start here with version 1 versus version 2. Let's pull up the codes for those ones quickly. Recall then that version 1 up here, which has pointers to structs, versus version 2 makes use of actual structs by dereferencing and then calling functions that are appropriate to them. So over here it's asking to examine and then just pick one of these options that best fits this. So V1 uses pointers structs while V2 dereferences to have local copies of the structs. That sounds good pretty far. V2 runs slower due to requiring more overall memory to store a second copy of the struct. Well, in our ordering a moment ago, it seemed very much so that the struct version here actually ran faster. It took less time, half the time more or less. And to that end, this first option can't be it then. Let's see, V1 uses pointers structs while V2 dereferences to have local copies of struct. V2 runs slightly faster due to some data being cached in registers rather than main memory. Yeah, that seems to fit right here. And that's the general MO that by dereferencing, you encourage a register to be used for a particular sort of value rather than hitting main memory through those indirect assembly instructions. So this one seems very plausible. I'm going to tentatively mark it right now while we consider other options. V1 uses function call while V2 uses a macro call. That does not seem to be the case because you can see clearly here there's a vsetp, that's a function call. It's being used in version 1. But these vsets s and getS, they're employed down here. These are still normal function calls, so that can't be it. And trick question, these two versions are identical. Zibby structs, and there's no difference between behavior between pointers structs versus local actual structs. That's patently false. So nice try, but we're going to stick up with this answer for now. That the primary difference is this is of pointer structs versus actual structs, and that will likely lead to more speed by putting parts of those structs into registers, because registers are faster. So the next part explores eventually the difference between this version 2 and version 3, but has a little bit of an interlude here to discuss the preprocessor part of the compiler. So this a command run here with this -E option, allowing us to stop, not at the assembly level, but actually much earlier, at the point that the preprocessor is finished with the C program. It's the entity that is responsible for saying, you've got a pound include or a pound define, I'm going to insert something in the spots that's associated with that. We'll take the output of that preprocessed C file, which is normally just printed to the screen. In fact, I can sort of show you what that looks like. If I come over here and open up the shell, then it just sort of floods onto the screen and makes it a little bit hard to read. So we'll pipe that into a preprocessed .c file, which we can then look at in the text editor. So right on the screen, it went into a file, and if I refresh my directory, the most recent one up here is preprocessed.c. So open that up. This is a C file, but it has a whole bunch of stuff in it that is not necessarily stuff that you would normally look at. These pound things are sort of interesting, and we don't need to dwell upon them too much. But as you scroll down, you'll start seeing type defs that are not necessarily something that was present in the earlier C file. In fact, there'll be lots of things in here that may be slightly foreign, but if I'm not mistaken, we can poke around and find, there's a printf function, an fprintf function, an sprintf function, of various printf functions. And the place that these declarations of the existence of such functions that it's coming from is actually from, if I pull it up, from this pound include of stdio up here. Basically, what pound include does is goes and finds this file, stdio.h, on the system, wherever it is, oftentimes in some system directory that the compiler knows about, and inserts the entire contents of that .h file in at the top up here. We might even be able to find, it's up here, this declaration that the following contents came from stdio.h. That was in the system directory user include stdio.h. Later on, there'll probably be some other sort of directives saying like, oh, the next things came from that file as well, or from other sort of pound includes, etc. But essentially, this pound include system is just a glorified copy-paste, copy the contents of this file in here. Now, what that does is make the compiler aware of various things like, oh, there's this putcar function. There's this putc function. It's right here in this preprocessed C file, which is going to be fed into the compiler later, so that the compiler is aware that, oh, if you use this function or this function or this function later on in your code, then it will know that it's used correctly with the calling conventions and return types and so forth, or incorrectly. And so that's all the header file system is copy and paste header files into later files. Now, if I do a significant amount of scrolling here, and if I actually turn on line nums, you can see we're already at 1700 lines of code versus the original version was itself only a couple hundred lines of C code. You can see that the preprocessor actually inserts a lot of stuff in here, and I have to scroll significant ways down to finally find the main function that we're interested in, as this is where the stuff actually gets kicking. Now we're going to consult and compare differences between this left-hand side macro stuff over here and the right-hand side stuff. And to stay oriented, if I position it about here, in between, in our original version, the row sums func s and the row sums macro versions of these functions, there were these macro declarations. When I buzz over here and look for those, you can see up here the row sums func s. There's a gap here, because the macro definitions are no longer needed or present. Instead, code that they represent has been copied and pasted in. Up here, you can see function calls are handled just normally by the preprocessor. It stripped out comments here, but it didn't change the function call at all. However, the point that I made these capital macro call invocations, you can see that looks markedly different over here. That instead I have a template defined in this macro, and that template has been substituted in over here to sort of paste stuff into this spot. This is why the parentheses become important, because whatever is passed in as this for first parameter is going to appear here, and that could be some addition or something like that. Make a little more sense in a second. But at any rate, the macro definitions are gone, replaced by inlining that code at the call sites for those macros. To boot, if I come down and look at this pipelined, or say this unrolled version over here, you can see then the j plus 0 here, that entire thing has been substituted into this little parenthetical over here, and so too for j plus 3, etc. So in that respect, this whole bit of business then is, again, a glorified copy-paste. Anytime you see an invocation of mget, paste in the definition for that thing and expand it, as it were. I think it's the technical definition is a macro expansion. C has a fairly limited macro expansion set of facilities, but other languages like Lisp feature prominent macro systems that are very flexible. But it gets to the heart of sort of, do I jump to another location code, or do I take that code and jump the code itself into this spot? Basically distinguishing between a function call and a macro invocation, those two things. All right, so then let's return to our questions.txt, because we're probably in a position to answer some stuff. So after running this command and looking at preprocess.c version, then let's see what appears to be the first few thousand lines of code in the preprocess file. Lots of C type declarations, etc. for A to I and so forth. That seems like it might be it. It's definitely not assembly instructions. And it's definitely not a translation of the original into assembly instructions. Instead, this is those pound include declarations that are up there. Cool. So we looked at the end here, and we're looking at this V2 versus V3 version. And this V2 version had function calls in it, and it was not changed very much. Body mgf, nope, okay. And what about the row sums macro version? It's these bodies of this mget and vset, they've been subbed in. It certainly has changed, and there's no assembly involved in this thing. Now, when the compiler gets to this then, it'll see this code and insert appropriate assembly instructions, just as up here in the earlier not the macro version, but the function versions, it would insert a function call here. We observed in our timing that these two things, if I just run it again over here, have a time difference as well. That version 2 that uses a function call is somewhat slower than the macro version. And it's worthwhile to consider why exactly that is. So which of the following reasons are valid for this tight computational loop benefiting from the macro invocation. Or rather, in this case, it's asking why is calling a function interfere with the ability of the compiler to optimize. And that would explain then why doing the straight line code in the macro, if we could figure that out here, is faster in some way than this. Now, oftentimes, students start out with like, well, there's no place to go here. Like all the code you're going to execute, it's present here. Versus the function call up here, this involves a control flow change. So I've got to jump up here to this mgetS function and do it, and then jump back. Keep in mind that modern computers, particularly for function calls like this, they're pretty good at optimizing control flow performance. So while it's true the RIP is going to sort of move around non-linearly, this isn't that big of a deal. Somewhat more pernicious is the need to push a return value into, or a return address into the stack for any function call. That means a main memory interaction. If we're trying to reduce sort of the burden and do as much as possible in registers, then pushing a return address into the stack or before you call this, so you know where to return to after mgetS and come back over here, That is not needed at all in the macro version, which has inlined this stuff, and therefore doesn't require either the control flow change nor the interaction with main memory to push a return address in. Finally, and this is possibly the most pernicious part, you'll recall that there are certain conventions associated with register use. And if I just get this thing up here, calling mgetS here requires me to push the arguments to that function into registers, so this mat structs and the I and the j indices. In addition to that, there's a set of caller save registers that may change during the execution of this function. So the RDI, the RSI, the RDX, the RCX, the RAX, the R8, R9, etc., all those registers may change across this, leaving very few registers up here within rosum's func S to be available within this code to sort of do things. Instead, we have to spend some time to push all of the call save registers that you might want to use in to preserve values across this function call and use those. So it takes time, leaves fewer registers to do things, and is generally sort of not as efficient. The flip side down here, when you inline that code, there's no change to another function, and so all of the caller save registers remain available for use to store different things like indices or multiplication results or stuff like that. And that generally enables the compiler to much more efficiently pipeline things and exploits the available register file as much as possible. So if we jump over here and considers, see, calling functions requires use of specific registers for passed arguments. That's definitely true. Let's see, calling a function means that all callee save registers might change. Yep. Jumps control different paro, which puts more pressure on instruction and data cache. That's probably true. Actually, all these reasons, that's fun called by some observations. Oh, you did it to me again, Kaufman. It's like actually all of these. So we'll mark that one down and space out our previous ones up here. Function calls themselves then, not too bad in terms of the control flow, but when you're looking for optimal code, you try to avoid function calls as much as possible. To that end, we're going to return to our original C version here and finally consider this loop unrolled version down here, which the following best describes the difference between the code in v3, the macro version, and the v4, the sums unroll version. v3 iterates through each matrix row by one element at a time, while v4 iterates 4 elements at a time. That part is true. Let's see, is this going to be in all of these things? I bet it's going to be in all of these things. v3 adds on a single row element to a single sum per iteration, while v4 adds 4 different elements 4 times. Yeah, this is definitely going 4 at a time in the main inner loop here, and adding on to 4 separate variables. So I think I know where we're headed with this. Because of the looping pattern in v4 requires a second loop to finish elements. Yeah, we sort of alluded to that fact down here, that should the array not be evenly divisible by 4 in its length, then I'll have to iterate a few extra times to catch those last elements down here. So this looks like an all of the above situation rather than none of the above. And the best explanation for why this improves performance? Well, with 4 separate arithmetic operations over here, if I had 3 or 4 ALUs, I could do all of these operations simultaneously, so long as I have the data available to me. We're visiting cache in a favorable pattern here, going across a row. And so fetching the first element in a cache block, if it's a miss, will load subsequent elements in, and they can then get data into the pipeline for use or into a set of multiple ALUs fairly quickly in order to keep that processor fed with data. So to that end, we can do more things at a time then, get more instructions per cycle in this later version, which plays out then in practice, as we saw in the timing, that the fast version of this is the unrolled version. Keep in mind, though, that if we were going down columns or instead hitting main memory hard, this unrolling probably wouldn't provide any benefit. And it's interesting to explore, what if I took the original version where I had pointers to things and unrolled it? Chances are likely you'll get little to no performance gain, and in some cases may actually hurt performance because you put more register pressure But things as they are now, this v4 is definitely faster. Looping pattern favors cache. Actually, both of them have the same looping pattern. They're both going across rows, so that can't be it. However, each loop iteration has more independent arithmetic operations that can be executed. Favors efficient, so execution pipelined or superscalar processors. That sounds like a winner. And v4 is definitely not slower, so it's not any of that stuff. Cool. Let's do some quick checks. So if I fire up the shell, do a make test, which will test the code and the quiz. Oh no, let's see, what did I get wrong over here? It's probably a testing problem that Kaufman introduced. Say, oh yeah, okay, so I just need to update my test to include the, there's a bad sort of printing name over here. But I'll do that shortly, and the version that you get should be okay with that respect. Before I leave you, if you're in a hurry, you can definitely bail, but there is one more file that's optional to look at. It's called moremacros.c. I'll spend just a minute to have a look at it. It is here, moremacros.c. There are several things in here that are sort of dumbed down versions of some of the stuff that we saw there, but also a few new things. For instance, there's a pound include up here, so we'll expect a bunch of stuff from SDIO to be brought in, but also a pound-defined global constant called aconst. This is a typical usage for pound defines that are not parameterized, that just say this symbol will have this meaning, used all over the place. It does have a slight difference than a sort of typical global variable. And we can see that once we sort of launch the preprocessor. So I'm just going to copy, paste this thing, blast over that preprocess.c file, and I'll pull that back up here. Let's see, sort of towards the end here. So you see, just as before, there's a bunch of stuff up here that has been inserted from the stdio. And then the function definitions for this compute, but there's no aconst anymore. Instead, the 15 that was parameterized as, down here, that 15 has been pasted into all the locations that it was at. So here's the 15 for A rather than aconst. Here's the 15 in the printf down here. To that end, this is showing one of the sort of drawbacks of the pound-defined stuff is that in the preprocessor source code, when you'd, for instance, be debugging it, maybe at the assembly level or something like that, you have no symbol anymore, and instead you just have a 15 there. However, this is still preferable to like inserting 15s everywhere in your code, that you pound define it up here, so if later on you realize, oh, 15 is the wrong number for this, I need 17 or 22, then you can easily sort of change this to a 22 over here, and every place that aconst appears, that 22 will then sort of be reinserted there. As well as providing a somewhat more readable experience where this is a symbol name rather than a, quote, magic constant, end quote. And generally just random magic numbers that appear in code is distasteful and oftentimes leads to problems later on. We're like, why was it 22 here? I don't remember. It's like we have to go find all the 22s, but it turns out there's 122 million of something, and so that 22 is not the one you're looking for. It's a pain in the butt. So generally more readable and more flexible to change. But no memory location associated with aconst. It's not a variable, it's just a substitution there. Similarly, there's a parameterized macro up here for this ABC. Seems similar in ways to the compute fun up here, except that the macro version, as you can see over here, gets inlined straight away. We'll talk in lecture on Wednesday about how inlining is actually something that the compiler can do for you, that it can sort of not bother with macros. You can just take this function definition and insert the code associated with it here, which is usually something you want to leave to the compiler, and we'll talk about trade-offs from there. The final one that I think is interesting, particularly for debugging, that's I don't think widely known to students at least, is that the C standard provides a couple macros. It's either C standard or GCC, I can't remember which. It's underscore underscore file underscore 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 line underscore underscore. Those symbols, they aren't defined within this. Instead, they're provided by the C compiler environment. And they're useful for debugging, so that, for instance, you can do a printf of file %s line d, And this will insert for that file, the file that you're in presently, and the line number that you're on for it. Tremendously useful for debugging, so that, for instance, I can just copy and paste the same thing here to sort of see locations. And if I GCC this thing, so sorry, take off this thing, GCC macros.c, and run the a.out associated with it, you'll see here I'm at line 27, and indeed this spot over here, if I bring up line numbers, this is line 27, but the exact same code down here is at line 36. So you can more or less copy this, paste this thing in at certain spots just to know I'm in there, or make it more sophisticated. Say I'm at this line, this file, this line number, and I want to print out some variables of some kind here for debugging purposes. These two macros then substitute for the current file and the current line that this symbol appears upon, making them great for debugging messages like that. All right, that's all I got. A few fixes from my part within the make file and within the testing code to get that right, but then we'll be all sorted out. And if you made it to the end of the video here, you should be able to submit having learned something and earn your engagement point. Hope everyone has a wonderful Thanksgiving, and I'll see you after the break.